collection of fabulous jerseys. All right, so optical isomerism was the last one we talked about. It's the hardest to spot probably because the structures are very, very similar looking. When you draw them, if you draw the structures, it's really very tough to see the difference between the two. They are the optical isomers are also called enantiomers. Enantiomers is another word for optical isomers. Again, they're non-superimposable mirror images. And the most common place this shows up, it's not the only place, but the most common place this shows up is if you have a tetrahedral atom. So it could be a carbon atom. It could be a zinc in a zinc 2 complex or something with 4 different groups. So like you built the last time, so you could see it. Here are 4 different things attached to the same tetrahedral central atom, and its mirror image would be the other enantiomer. And it's tough to spot if you're not aware of what you're looking for. And like we mentioned right near the end the last time, if you built, say, this complex ion of zinc with 4 different halogens and its mirror image, if you set it down so fluorine were at the top, I don't know which one's fluorine, doesn't matter, and you walked around the bottom of each of those clockwise, you see the atoms on the bottom in a different order, right? You see chlorine, bromine, iodine, sort of in periodic table order. In the other enantiomer, you'd see chlorine, iodine, bromine as you walk around the base clockwise. So they're different. Even though they're mirror images, they're different. Like we mentioned, amino acids, 19 out of 20 amino acids found in proteins have the possibility of enantiomers. Glycine is the only one that doesn't have enantiomers because it has 2 identical attachments to the carbon there. It's 2 hydrogens. But otherwise, the other 19 amino acids that you find in proteins could exist as one or the other of a pair of isomers, and that's where the chemical properties are different. Optical isomers and enantiomers have different chemical properties in environments containing other optical isomers. So if you eat something that's, some synthetic supplement with amino acids and it's the wrong isomer, your body won't be able to use it because your body's made of proteins that use the other isomer. And this is true for a lot of things that involve isomers. And this is where, if you draw those line angle structures of an organic molecule, recall with like dissolves like, we had vitamin A, vitamin C, which one's water soluble, which one's fat soluble, and those line angle zigzag structures. Sometimes you see a bond that's drawn with a wedge or a dashed shape. And that's because, like we have on the zinc complexes here, the wedge or dash shape is often drawn in those kinds of structures because the geometry is important. Because they're trying to show it's this isomer or that one of a pair of optical isomers. So we do that if we need to. Also, optical isomerism occurs in other places. In octahedral complexes, where you have multiple bidentate ligands. I'm trying to get it so it's not falling off, but I guess it's the best place. If you have 3 bidentate ligands on a octahedral central atom, for example, if I had 3 ethylene diamine ligands, if I draw the octahedral, basic structure here, if I have 3 ethylene diamine ligands, again, the curved lines simplify life because it just means, there's a CH2 on there. That's fine. There's one of the structures I could have for ethylene. It's going to be tris ethylene diamine iron 2 ion. I need 3 ethylene diamines has a +2 charge because ethylene diamine is neutral. But if I had a mirror image of that, imagine mirror on the wall, the other isomer, it's really tough to spot this probably. As it happens, all the donor atoms are nitrogens. But let's see, this would reflect to this, and this would reflect to this, and this out here would reflect to that. If you build that, it turns out it's not superimposable. It's hard to visualize this. It's tough to see without building. No one box of atoms and bonds probably has the right things to build this. But the analogy for this would be if you had opposite threaded screws or bolts or something. We used to have a nice pair of enantiomers in the men's room on the 4th floor of Night Chemical Lab. They've replaced the faucets for some reason. They still have the same faucets downstairs on the 1st floor. But on the 4th floor, the men's restroom down the hall from my office, there were 2 sinks. There's some other fixtures in there, and there's 2 sinks on this vanity they put in, and the hot water faucets turned opposite directions to turn on. Nobody knows why this was done, if it was factory seconds or something. But one of them turned on in the direction that usually, lefty-loosey, righty-tighty. One of them turned opposite that. And it was a good way to splash yourself with water when you think you're turning off the hot water, and instead you're just turning it on harder and faster at yourself, right? And they're optical isomers. That is a pair of enantiomers. The 2 things that are threaded opposite each other. They make those, right? If you have something that's going to be used, some kind of screw or bolt where an object is going to rotate, and they don't want it to unscrew itself because of the forces applied, they make backwards threaded screws and bolts. These exist. Fan blades is another example of that. If you have a fan, the blades have some curvature usually to force the air. You could have the mirror image of that fan. It would blow in the opposite direction. So propellers, fan blades, screws or bolts, they can be threaded either way. They're not all lefty-loosey, righty-tighty. They would be an analogy for this. This would look kind of like a 3-blade fan if you built this as a model. And its mirror image would have the opposite direction of threading, so to speak. So those are optical isomers. Those are enantiomers as well. It does occur for octahedral. It isn't just for tetrahedral. It's most commonly for tetrahedral because there's lots of tetrahedral carbon in our world. These are enantiomers as well. So that's good to be aware of, that they exist. Admittedly, it's hard to visualize, but it's easiest if you think about that. That's literally sort of like a molecular level, 3-blade fan shape that we have there. Can you have cis-trans with octahedral? Well, we're talking now that we've learned about all the different kinds of isomerism a little bit. Can you have cis-trans in tetrahedral geometry? Is there such a thing as cis and trans isomers? That humming sound again. There we go. Can you have cis-trans if something's tetrahedral? Like I've got the red atom in my hand here. Is the white atom cis or trans to it? Well, it's neither, right? It's the cis-trans has got to do whether it's across or next to. The blue, green, and white are all 109 degrees away from it. There's no cis-trans there. So you don't have cis-trans in a tetrahedral geometry. Not in a very simple geometry like this anyway. I suppose if you had very complex ligands somehow or something, people could start saying, well, it's cis-trans-like. But no, you can't say that the blue and the red are cis to each other because they're next to each other. Well, so are the red and green. It's not. There's no cis-trans there. Cis-trans is found in square planar, in octahedral geometry, but not in tetrahedral because it's a different geometry. So that's a point that comes up sometimes people are less sure of. How are we doing so far on the optical isomers? What questions have you got? Sort of worry about them. It's good to end on them so people can stew over them a little bit. By the way, what's optical about optical isomers? I don't know if that's still sitting on there. Oh, it might be. No, I guess used to have those, but they disappeared long ago. That's too bad. I don't know. Somebody found them, liked them, kept them. Oh well. Somewhere. Let's see if we have any more of those filters. What's optical about a pair of optical isomers? If you have a pair of optical isomers, if you have a pure solution of one enantiomer, and you take plain polarized light, if you have light has, like sunlight, it has electric and magnetic fields oscillating in all different directions. If you put it through a polarizing filter, like a pair of polarized sunglasses, it filters out everything except the ones that have the oscillations in a certain plane. If you took that plain polarized light and let it shine through a pure solution of one enantiomer, the light would be rotated x degrees to the right. The other enantiomer, a pure solution of that enantiomer, would rotate the light negative x degrees. It would rotate it to the left, the same amount. And so that's what's optical about optical isomers, is it rotates, a solution of an optical isomer rotates plane polarized light. The two isomers rotate it one way or the other. This leads to naming the optical isomers. Sometimes they'll name one of the isomers the D isomer, one the L isomer. And that has to do with, does it rotate the light to the right or the left? That's beyond what we're worried about at the moment, because we're not going to have to deal with them to that extent. But they end up naming them. So these two isomers up here for the zinc complexes, if you know enough about them, you could say which one's D and which one's L or something. It's not something that we're going to have to do. But there's got to be some way to identify them, right? I mean, they have to have, at some point, names that identify which isomer it is. And that's how it's done. So that's what's optical. Optical suggests that there's something to do with sight or light or something like that, and that's what it is, how the solution of that enantiomer interacts with light. So anyway, that's the last word on optical isomers. Sure there's not questions? You can always, if you want to play with those models sometime, if you're saying, gee, I'd like to build the models again, I didn't get a chance to use them myself, the person near me was hogging them or something, we got them in the back room. You can, borrow one or something. You got to promise not to dump it on the floor and let your cats eat the hydrogens or something. So, all right. One application that's interesting, among many, with coordination compounds and transition metals is anti-cancer drugs that use platinum. These are a classic kind of cancer therapy. There are fancier things that might be possibly less on the side effect side and everything, but it's a pretty classic class of cancer drugs. A lot of research goes into cancer stuff. The 100 days from today is the Velosano ride, so my butt will be sore after the 50 miles on July 23rd, I think it is. So it'll be terrible, but be trying to raise money for cancer research. But these compounds called cisplatins actually were discovered by accident. It didn't involve people riding their bikes 50 or 100 miles to raise money and stuff to do the research. They discovered it by accident. Somebody was doing a study on a different thing. They were talking about studying the effects of electric fields on mitotic cell division. So how do these cells divide if we apply an electric field around them? And they had this cell culture that they would spread on a gel. The gel had ammonium chloride as the electrolyte, and the electrolyte was there to allow the electric field to form. They had platinum electrodes, which are usually inert platinum electrodes, and they would connect it to a small voltage, and there would be an electric field. And the ions could migrate through this electrolyte solution of ammonium chloride. And what they found was near the electrodes, the platinum electrodes, the cells were dying. They were killing the cells. Something was forming. And it turned out that the so-called inert platinum electrodes were reacting with stuff in the ammonium chloride electrolyte that was in the gel, forming the cis isomer of this diamine dichloroplatinum 2. So this only works if it's the cis isomer, it turns out. The trans isomer could also be formed, but it wasn't causing this kind of reaction. They traced this back. They studied the structure. They studied the biochemistry of it. And it turns out there's actually a large number of different compounds in the class of compounds called cisplatins. Cisplatins involve a platinum 2 or platinum 4 compound with two cis ammonia ligands. So like we talked about the other day, we had the two ammonias, the two chloride ion ligands. The ammonia is cis, means the chlorides are cis. But it has to have two cis ammonias. And what goes on in these anti-cancer drugs is that the cis isomer, which has two chloride ligands, is a neutral coordination compound overall. One of the chloride ligands can be replaced with H2O, which is a neutral ligand. So this species now carries a plus charge because we lost an anion and ligand and replaced it with a neutral. So now that complex has a charge, and that's important for making its way through cell membranes and stuff. Ions, electrolytes are able to pass through cell membranes and things in ways that neutral molecules are not necessarily able to. So you get this charged species that can make its way through cell membranes. And this aquated derivative, boy, it's very technical language that turns people off, right? What the heck is an aquated derivative? That means, it's the subsequent molecule or ion that's formed by aquating, replacing something with water, right? So this is the aquated derivative here. It's a second structure. We've just replaced a chloride with a water. That binds to adjacent residues of guanine, one of the bases. Oh boy, I'm going to try to cartoon a DNA. This will be an entertaining misadventure. All right, I'm trying to draw, it's one of the better ones I've ever done. I'm trying to draw a cartoon double helix. Don't laugh. People are laughing. Don't laugh at my double helix. Okay, that's the best I can do. I'm not an artist. If you remember A, C, T, and G? This was on the Jeopardy the other day. As I recall, they had A, C, T, and G, and they changed like a T to a C, and it was something to do with mutations, was on the Jeopardy. If you have two Gs, G is guanine. If you have two Gs that are on the DNA in just the right place next to each other, and so I'm just going to label where they are, those bases, the guanine, they should be hydrogen bonded to the other strand, right? So I'm just labeling, I'm not saying that they stick out literally, I'm just saying where they are. It's cartoon more than it is anything. But this aquated derivative can bond to that location. The ammonias are still cis. And bond to the adjacent guanines. And when the transcription process occurs, you have this complex that comes along, breaks the hydrogen bonds, separate the strands, and you make new copies of the DNA. It hits this, and this screws up the transcription process. Kind of like it's sort of the molecular level situation of your zipper getting stuck because there's a couple of broken off zipper teeth stuck in it or something. It won't unzip. Well, there's two possibilities for your zipper, right? You either fix the zipper, you try to break those teeth off, or you toss it out. Same thing here. When the transcription complex gets here, it's either going to fix the damage, or it's going to start the programmed self-destruct sequence, apoptosis in biology terms, the programmed cell death sequence, where it says, something's wrong with the DNA, there's a problem here, do the James Bond self-destruct button and hop in your cello and slide to Austria or something. So this is going to hopefully kill the cancerous cells. You have to target this stuff if you can to the cancerous cells and program the cell death. There's an article from the Journal of Chemical Education on the website with the notes. It's a little technical. That journal's pretty good for being an accessible level, though. But it's got some better artwork than I can draw. It's got a nice figure with when it gets to the DNA, and it says two options, repair, DNA repair, or programmed cell death. And there's a cute skull and crossbones and everything with the programmed cell death. But these platinum compounds, they're not perfect. They have a lot of side effects. A lot of it can get taken up into other places before it gets there, but it's pretty effective. It's been very effective for use of treatment of different cancers, including testicular cancers. We know Scott Hamilton around here. He has had a lot of treatment at Cleveland Clinic. He's the figure skater from the Olympics a number of years ago. Lance Armstrong, like him, hate him, whatever. Also used cisplatins, but they're a classic cancer drug, and it wouldn't work if it were the trans isomer. That's what's important here. If it were the trans isomer, this attachment part here, it wouldn't work, right? They wouldn't have the 90-degree angle at the platinum to form the bonds to the guanine bases. So it's a pretty important thing that it is the cis isomer. So that's it's easy to ask on the exam too. You'll see there's an old exam question on that old exam for practice that's related to it. You'll see. I don't want to blow it because it'll be good to practice with. But that's one example. Coordination compounds are in lots and lots of other places as well. In biochemistry and biology, your hemoglobin is an iron coordination compound. There are nitrogen donor atoms on 4 positions. The oxygen attaches to the iron as well. Also chlorophylls. Chlorophylls is one example of where it's not actually a transition metal. Chlorophylls involve magnesium ions. But magnesium ions can do this coordination chemistry as well, where they are surrounded by the nitrogens, and they're important in plants, right? You can't have the green color of plants without chlorophylls. We know in the fall, when the chlorophylls begin to break down, you get the other ophylls that have different colors. So plants and animals both count on coordination chemistry for a lot of important things, for hemoglobin, for chlorophylls. And the similarity between chlorophylls and hemoglobin, it's in the text if you're reading a little bit of it in the chapter. The similarity between those two is very striking. The similarity around the metal atom, whether it's iron or magnesium, by the structure where the 4 nitrogens are connected by other things that go out. Really amazing. Porphyrin rings, they call them. Can't get the second P. It has a PH that oh, now it's going to erase. Porphyrin. It's an easy word to write if you have a stick that's cooperating. So metals in porphyrin rings are found in hemoglobin with iron and chlorophylls with magnesium. All over the place. Kind of neat. I did some research when I was an undergrad with substituted metalloporphyrins. This is near and dear to my heart. I never got anything as a product except black tar. You're supposed to get nice purple crystals, and I'd always get black tar. And we'd run spectra on it, and the compound I wanted was in there, but I could never get the crystals. Oh well. Years later, I found out somebody had replaced the purple crystals with Folgers crystals to see if they were rich enough. I wish they would have told me. I would have told them I don't drink coffee. So this is coffee to me. So I'm vamping for questions. Make sure I see. Okay, no, okay. All right. So check that article out if it's of interest. It's got a little more technical detail, but it gives the same story with a little more detail. The artwork in that Journal of Chemical Education article is pretty good. I'm not sure if I have it saved on this computer or not, with all the computer changes over the years. I'm not sure. It's on the web, though. Okay. Then the next item on our list of things to do, and we're right on schedule with the syllabus, believe it or not, is Chapter 24, Nuclear Reactions. And it's nuclear, by the way. This is one thing that drove me nuts. I liked the TV show 24. I loved the TV show 24. I hated how Jack Bauer would talk about nuclear. Say, a nuclear bomb's going to go off if Chloe and I don't stop. No, nuclear. Oh, God, I hated it. Otherwise, I love that show, but he's got to say nuclear, okay? So you want to drive me, it's worse than fingernails on a chalkboard when I hear nuclear. Oh, I hate it. I don't know how that happened, but whatever. I know language is organic. I took a linguistics class. I know language develops this and that. Yeah, but still it doesn't stop it from driving me crazy. So nuclear reactions and their applications. This is at the end of the book because in all the other 23 chapters in the textbook, we deal primarily in chemistry that is determined by the number and arrangement of electrons. The protons and neutrons are outside, the protons and neutrons are inside the nucleus, the electrons are outside the nucleus. And so in most chemistry, if we're talking about redox, acid-base, Lewis acid-base, Bronsted acid-base, we're talking about any ordinary chemistry of metabolism and respiration and all these things, it's all based on the electrons. In Chapter 24, we look at nuclear reactions, where the protons and neutrons in the nucleus are part of the reaction. It's a different kind of reaction. There are some people who teach the Chem 2 class and say, I don't do nuclear reactions, or I don't like doing nuclear reactions. I'll do it for 40 minutes or something just so I can say I did it. But this is physics, not chemistry. But it does pertain to atomic structure. It really is related to the chemistry. And it says in the catalog description of the course that we cover it. So it should be done. But it actually brings in a few things that we've talked about before, and it's related to atomic structure. It's really important. The energies associated with nuclear reactions are millions of times or more greater than those ordinary chemical reactions, and this is current events related. with things like nuclear weapons, and nations like North Korea, and do they have them? Do they want them? Can they get them? This and that. If you know people who live over in that part of the world, I have a friend who just finished basic training in the South Korean military yesterday. Now he's got to do 23 more months of service. He deferred it for a while because he was working at Sherwin-Williams in Cleveland until the fall. But he had to go back to Korea to do his, and that's one thing that's on their minds a lot is nuclear reactions, because in the hands of the wrong people, these can be kind of dangerous. So we want to understand these things. It's a good thing to be familiar with and understand. So we got to go back to chapter 2 for some information that we haven't needed to deal with a lot since, like, chapter 2. Some terms that you might recall from chapter 2. If you don't, we'll hit them right now. So things about isotopes and nuclides. Some of these words are new, some are not. Okay, so we'll have to hit them all so we remember them.
What do you say is the most dangerous thing part of nuclear reactions? What's the most dangerous part of nuclear reaction?
Oh, well, it was all going. Depends how close you are, huh?
The force, or is it like the kind of...
No, it depends. There's so many different kinds of radiation too. We'll talk about them a little bit. About you can be near a smallish amount. It doesn't have to be an explosion. You can be near a smallish amount of something that's a neutron emitter, and it'll kill you. And that would be more dangerous than being a fair distance from a above ground nuclear weapons test or something. Even possibly, it depends. It depends on a lot of factors that go into it: the kind of radiation, the distance, how much exposure. Yeah, but if you because people live near a nuclear power station and are okay. But if you were, if I was sitting here if this were emitting neutrons, I would be dead in a minute, probably, if not already. Because neutrons we'll talk about the different forms of radiation a little bit. So, depends, they always have these scary, what if someone had a suitcase-sized nuclear weapon and detonated it outside the Capitol building in D.C. or something, If you're this close, you'd be vaporized. If you're this close, you'd see the flash, but die before the shockwave got to you and everything. It's very depressing. It's very scary, right? But it's probably one of these things where you either want to be real close or very far away. If you're in the middle, then you get the effects. Then you get the effects of the radiation while you're still alive, which is, So it depends. Depends on a few factors. The distance, the time of exposure, the type of radiation. So there's no one thing. If I had to choose which kind of radiation to be exposed to, I would not want, say, neutrons or something. That would be bad. But so neutrons, protons, electrons, remember those? Sort of. We haven't had to deal with protons and neutrons a lot lately, right? We've dealt mainly in like 1s2, 2s2, 2p6, all the electron configuration, charges on ions. So the atomic number. Recall the atomic number, symbol Z, capital Z is the symbol for atomic number. It's the number of protons in the nucleus of an atom. It's kind of redundant to say in the nucleus. That's where they are, right? Protons are in the nucleus always. So are neutrons. The mass number, capital A, tells you the number of protons and neutrons. Yes, A is not the symbol for atomic number. No one, can explain that other than to say that some of these things came from stuff in other languages, and sometimes the letters are already used. So, for example, if we were to write this as a symbol, here's the symbol for a particular kind of atom here. That symbol has the atomic number on the bottom, the mass number on the top. So mass numbers on the top, atomic numbers on the bottom. So that's how we write those. Mass number on top, atomic number on the bottom. How many neutrons are there in that atom? We know it has 6 protons because the atomic number is 6. How many neutrons does it have? 8, right? The top number is protons and neutrons. The bottom number is just protons, so you subtract. They're lined up for subtraction here. 14 minus 6 is 8, right? You could have them right there, subtract. So 8 neutrons in an atom of this kind. We would call that, as you might recall, we would read that as carbon-14. You always say the name of the element first, even though the mass number is to the left, a superscript position. We would say that this is carbon-14. Elements are not proper nouns. They are not capitalized unless they begin a sentence, even if they are named after people. So if you have a nice Einsteinium or something, is still the element name is down, unless it's the first word in a sentence, then it's capitalized. So carbon-14 has 6 protons, 8 neutrons. It also has 6 electrons if it's a neutral atom, right? Because it's got to be neutral as an atom. It has the same number of electrons as protons. Okay, so that's review from chapter 2 so far, right? We know that, but we haven't needed to use it lately. It's been so long since you've needed to use that, probably like the final exam of Chem 1 in December or something, since you needed to even think about how many protons and neutrons. So got to bring this up now, because now we need to think about how many protons and neutrons there are in an atom a lot. Isotopes. Isotopes are atoms with the same atomic number but different mass number. So for example, carbon-12, carbon-13, and carbon-14 are 3 isotopes of carbon. We could have, say, chlorine-37 and chlorine-35. Those are 2 isotopes of chlorine in naturally occurring chlorine. But what if I were talking about, I don't know, helium-3, copper-63, and carbon-13? Those aren't isotopes, right? Because they're not atoms with the same atomic number but different mass number. What does it mean if they have the same atomic number? What's another way to say that? If they have the same atomic number, they are of the same element. Yeah, same atomic number means same element. But different mass number. So same Z, different A. So the top number changes, but the bottom number doesn't, which means the symbol doesn't. So if I got a hydrogen, a helium-3 and a copper-63 and a carbon-13, I can't say, here are the 3 isotopes that we're going to deal with, because those are not isotopes. It seems pedantic and annoying, but it is correct. It's technically correct, which is the best kind of correct, to say those are not isotopes. Those are atoms of different elements. They're not isotopes. So isotopes have the same atomic number, which means they are atoms of the same element. So to get a word that we could use to describe atoms of different elements that have a particular mass number, we have a new word that we probably didn't see in chapter 2. So this is new to you, vocabulary. Nuclide. A nuclide is a single type of nucleus. And if you have nuclides plural, it would be a group of nuclei, of types of nucleus. So for example, we could say that, helium-3, copper-63, and why not, carbon-13 are 3 great nuclides. They're not isotopes, but they are nuclides because they're of different elements. So a carbon, a chlorine, a copper, yeah, they all begin with, they begin with C. A helium, a hydrogen, they both begin with H. That's all they have in common. They're not of the same element, so they're nuclides. We can talk about this nuclide, hydrogen-3, or helium-3, or copper-63, whatever. This nuclide has these properties, blah, blah, blah. It's awkward to say this isotope unless you say this isotope of chlorine, or of, it's pedantic, it seems, but it's important. If you look up data for the information that you might use in nuclear reactions, it's looked up on a so-called chart of the nuclides, or a nuclide chart. Okay, you don't always go to a periodic table. Okay, and it's not an isotope chart; it's a nuclide chart because it lists information for all the elements, all the isotopes of all the elements, and so it's a nuclide chart. So nuclide's the word, okay, for describing when you have different elements with different isotopes of each. Also, nucleons, also new to you. Nucleons is a collective term for protons and neutrons. We're going to worry about how many nucleons a thing has in a couple of different places. So nucleons is either protons or neutrons, doesn't matter, they're both nucleons. So for example, we could say that carbon-14 has, How many nucleons? 14. If I can get the nucleons word to come out of the pen correctly. It has 6 protons and 8 neutrons, for a total of 14. The mass number tells you how many nucleons. The mass number is the number of nucleons, right? Because the mass number up above is the number of protons and neutrons. Great how all these words sound alike, right? So protons and neutrons together is the mass number as a count, and as a collective noun, we use nucleons. So a carbon-14 has 14 nucleons. That's its mass number. That's how many protons and neutrons collectively. And the reason for worrying about nucleons is a few different places that we'll see it used. Yeah. Those are 2 different nuclides. They are atoms of different elements, so we wouldn't say they're isotopes. There are other terms that are less important. Yeah, we couldn't say they're isotopes. Chlorine-35 and sulfur-35. They are 2 nuclides that happen to have the same mass number. Yeah, is probably the most succinct way to describe them. Yeah, they're not isotopes because they're not of the same element. There are other terms that are not worth introducing, like there are isotones. Isotones are atoms with the same number of neutrons, not nucleons, and that wouldn't be them either, right? So if we have 2 atoms with the same number of neutrons, they'd be isotones. So like a helium-4 and a hydrogen-3 are isotones. We're not going to have to memorize that word. And the way people sometimes remember that is isotopes have the same number of protons with a P, and isotones have the same number of neutrons with an N. And then there's another word that's escaping me for things with the same mass. They're basically isobars. They have the same mass, or isobars, like the lines on a weather map. But we're not going to worry about those names, yeah. But for the purpose of what we're worried about, we'll just say those are 2 nuclides with the same mass number. They don't have exactly the same mass to a lot of sig figs, because they have different protons and neutrons. But yeah. So for purpose of this, we'll stick with saying they're 2 nuclides of different elements or something. Yeah. Oh, a nuclide is just a single. So the nuclide we're going to study today is technetium-99. That's a nuclide. Or if we have plural nuclides, it just means that they're not all of the same element. Like we're going to study carbon-13 and oxygen-18. Those are my 2 nuclides today. Or let's say we were doing carbon-12 and carbon-13. Those are the 2 isotopes that I'm studying because they're of the same element. It seems nitpicky, but it's mainly, so that you don't say the wrong thing to somebody and offend them. Yeah. So nuclide singular is just a good term to have, but nuclide plural is whenever they're of different elements. And that's why they say when they got this data chart that has, for every element, all the isotopes of each element, they call it a nuclide chart because all the elements are on there. Yeah. Seems nitpicky, but it's, it's the term we need. So yeah, those 3, the helium, the copper, and the carbon atoms, those are 3 nuclides. Because as a group, they're nuclides because they're of different elements. Whereas this list above, these are 3 isotopes because they are of the same element. Isotopes like the baseball team in Springfield. There's lots of Simpsons-related stuff that goes on with this, I guess because of the nuclear power plant. But you start getting those other words like isotones. Isotones, the joke on isotones, and I was learning this in Dr. Burmeister's class, actually, one time. Isotones, they said, was a failed musical group in the 1960s. There was someone in the Isotones. It was everybody in the... That's how the bands were named back then. Martha and the Vandellas, and there was somebody and the Isotones. So that'd be a good name. They should bring that back. But, oh well. So, okay, those are some terms that are old and new because we're going to use the terms. The nucleons, by the way, in the nucleus are held together by a force that is relative. It's called the strong force. It's called the strong force. I mean, they couldn't come up with a better name for it. Protons and neutrons are held together in the nucleus by the so-called strong force, which is much stronger than electrostatic repulsion. So 2 neutrons are attracted over short distances in the nucleus by the so-called strong force. So are neutrons, so is a proton and a neutron. It doesn't matter which particle it is. That's why the nucleus doesn't fall apart. Sometimes people wonder, how can you have all those protons in that small region, the nucleus, and they don't electrostatically push each other away from each other because positive charges repel? at the level of the nucleus, electrostatics are there, but there is this so-called strong force which holds the particles together. And it's a number of times larger than any electrostatic forces would be. So what goes on in nuclear reactions is something called radioactive decay. Radioactive decay is a process where a particular nuclide becomes a nuclide of something else. It might be of the same element or of a different element, depends on the kind of radioactivity, by giving off some kind of particle and some amount of energy. Now, the particle could be a largish particle. It could be a very tiny particle, a photon, which technically maybe not even is a particle, but recall photons. Photons are the matter-like packets of energy that are emitted as light. And, light has the photoelectric effect. Energy is quantized. These quantum mechanical photons behave like particles in certain ways. So you give off a photon, you could give off an electron, you can give off a neutron or a proton or a larger particle. So radioactive decay is some spitting out of some particle. It's a first-order kinetic process, at least to most approximations. People fight over, well, is it really first order or is it almost first order? It's close enough to first order that it's treated as such, which means that being first order, the reaction of radioactive decay for a particular substance has a half-life that's unchanging. Recall from kinetics, first order reactions have a half-life that does not change, does not depend on the amount of sample. And that's why we can say the half-life of carbon-14 is 5,700 years, and we don't have to say how much carbon-14 there was. We just know it as a half-life. Most nuclides undergo radioactive decay. If you're reading along in the chapter, which is a good thing to do, you'll see there's a table that shows all the nuclides in a graphical form with the number of protons and the number of neutrons on a chart. And most of the dots represent radioactive nuclides. They undergo some kind of radioactive decay. Relatively few nuclides are stable. Most are radioactive, which is fine. There's enough non-radioactive, enough stable ones to get by. The ratio of neutrons to protons determines a nuclide's stability. If the ratio of neutrons to protons is too high or too low, then the nuclide is going to be unstable, and it's going to radioactively decay to get to a better ratio of neutrons to protons. So I'm just going to give myself a blank space here. There is a graph which is better. I don't like replicating lots of graphs in the notes where you already have it in the book. Plus, often the graphs in the, if I import the artwork into the notes, there's often extra shrubbery on there that would get in the way. But the graph here, if I have the number of neutrons versus the number of protons, most of the stable nuclides are found in a band. And I'm not drawing points. I'm just trying to kind of pseudo shade an area. A band here that's about 1-to-1 ratio, but then starts to peel upward, more neutrons compared to the number of protons, until a certain point, and then it stops. So it's about 1-to-1 early. There's about 1 neutron for every proton early, and then it starts to peel upward, and it stops. There are no stable nuclides found above 83 protons, which would be bismuth. Bismuth has 83 protons. There are no stable nuclides found after bismuth. There are long-lasting, naturally occurring isotopes of some of the elements after bismuth. If you look on the periodic tables there, recall black print is solids, red is gases, blue is liquids at standard conditions. The outline letters are elements that are synthetic, that have to be made by people. They do not occur naturally. And we see that after bismuth, there is polonium, astatine, radon, francium, francium, whatever, radium, actinium, thorium, protactinium, uranium. There are a few naturally occurring elements that are in black type, or possibly red for radon, that are naturally occurring. That's fine. Then after that, they are all outline letters. They have to be made. They're synthetic elements only. Any of those have half-lives that are short enough that they're not found in natural samples. So we're not saying that there's no such thing as those elements. We're not even saying that they have to be made. But uranium, its half-life is about 4.5 billion years. It's about the estimated age of the Earth. There's plenty of uranium from natural sources still available because it decays so slowly. So anything above 83 in atomic number is not going to have any stable nuclides. Bismuth, it turns out, for a long time was thought to be stable. All isotopes of bismuth are stable. Turns out the stable isotope of bismuth, which is bismuth 209, you see on the periodic table, it's 208.9 something something. The most common isotope is bismuth 209. Turns out it is radioactive, but it has a half-life of about 2 times 10 to the 19th years. That's a 2 with 19 zeros after it. So that's way old. Half-life is, orders of magnitude longer than the, anything, right? So it's considered stable. It's observationally stable, they call it. Yes, it's technically radioactive. It decays too slowly to bother considering. So they consider it observationally stable, even though they know it's not. If you look up elements, some of them will say observationally stable, which is kind of a disclaimer that, well, if it does decay, it decays too slowly to measure. That one actually was measurable with a lot of very sensitive work, but, a 2 with 19 zeros after it for a number of years for the half-life means it decays too slowly to bother with. So we're going to say that bismuth 209 is stable. Everyone does, given that its half-life is, so long. Now, unstable nuclides will decay to produce stable nuclides. And there are sort of 3 different places a nuclide could be, right? A nuclide could be up here above this band of stable nuclides. If the stable nuclides are found in that band or belt or region or whatever term you like, an unstable nuclide could be above, or it could be below, or it could be beyond, right? It could be out here beyond the band of stability. And so which way it's going to decay to get to the band of stability depends, right? If it's above the band, it's got to go down and to the right. If it's below the band, it's going to go up and to the left. If it's beyond the band, it wants to go to the left and down. So there's 3 different ways that the nuclide wants to march to get to the band of stability, depending on if it's above, below, or beyond the band of stability. And we can predict the mode of decay based on that neutron-proton ratio. If it has too many neutrons versus not enough, it'll go one way or the other. And if it's above 83 in atomic number, we predict it might go yet another way. So let's see here. We have a list of types of radioactive decay. And these are worth being familiar with. These are some types of radioactive decay. These aren't the only types of radioactive decay. These are a few. Many of them use Greek letters. If you're going to use Greek letters, then the first on the list might as well be alpha decay. Alpha decay is the emission from the nucleus of a so-called alpha particle. And the alpha particle happens to be identical to a helium-4 nucleus. So the nucleus of a helium-4 atom, that is to say no electrons are attached, so it is technically He2+. That's the chemical formula of an alpha particle. It's helium-4 with a 2+ charge. We usually don't bother with the charge when we're dealing with this because that's going to find electrons. It's going to grab electrons from surrounding matter and become neutral, helium-4. So it's the other particle's problem to deal with the charge at that point. Uranium-238 is an example of an alpha emitter. Alpha emission is most commonly found beyond the band of stability. The heavy nuclides that are beyond the band of stability generally undergo alpha decay with some spillover into where they're above the band but can't get there by a single decay mode. So alpha decay is primarily for heavy nuclides like uranium-238. Look at the crazy chemical equation. It's not really a chemical equation anymore. It's more of a nuclear equation. We're only dealing with the nuclei here. We're not really worrying that much about the electrons. Like we said, the alpha particle is really a cation. The other product would be an anion, but then they transfer electrons around. So the U-238 decays by alpha emission to, it turns out, thorium-234. I think that's thorium, or is it thulium, or thallium, or no, I think that's thorium. TH is thorium, it turns out. TL is thallium, for example. So that's thorium. You don't have to learn all the names of these wacky other elements necessarily, but that's thorium. How do we balance this? Let's not worry about this over here at the moment. We'll get back to that in a minute. It doesn't affect anything with the balancing. You could not predict that. I have it there mainly because, for accuracy's sake, it is involved in this. We'll mention it in a second. But how do we get this? Let's say this were not given, and we asked, what nuclide is produced when uranium-238 undergoes alpha decay? You could figure it out. The numbers must balance. The atomic numbers must balance, and the mass numbers must balance. So given that it's an alpha decay, that's 4, 2, and a helium symbol, the other number has to add with 4 to give 238. So it must be the 234, right? So that's how we get the 234. And then the bottom numbers must balance it as well. So something plus 2 equals 92. Not exactly pre-calculus mathematics to solve that, right? That's 90. And then you go to the periodic table, and you find the symbol that goes with number 90. That's TH. So you don't even have to memorize that it is TH, right? You first get the number 90, then you go to the periodic table and find that 90 is TH. And even if you don't know the name of the TH, you know that it is from the periodic table. So that's how we get that product. And that's the so-called daughter nuclide. They call the other product usually the daughter nuclide. It's somewhat in deference to Marie and Irene Curie. There are a lot of women like Marie and Irene Curie that did a lot of the work with radioactivity in the early 20th century. Yeah.
How do you recognize an alpha particle?
So the alpha particle, well, how do I recognize it, or what do you mean?
Like, how can you tell it's an alpha particle?
Well, once the alpha particle forms and it gains a couple electrons to become neutral, it's a helium atom. It actually becomes a helium atom, indistinguishable from any other helium atom. And actually, as I was going to mention, a lot of helium is found underground, actually. It's not, helium escapes the atmosphere because it's a light atom and has a fast average speed. From kinetic molecular theory, it must have a fast average speed. Helium in the atmosphere escapes the atmosphere very easily. A lot of helium is found underground, and it's found underground in above deposits that contain rock that has things like uranium and other radioactive alpha emitters in it. And the helium is formed from alpha emission. So it's literally, once it gains a pair of electrons, it's a helium-4 atom, indistinguishable from any other helium-4 atom. And that's where we get helium for, blimps and balloons and stuff, literally, usually is underground deposits, where, it gets into a cave, crevice type area, and, it's found often in places with natural gas and other things as well. But yeah, so once it gains the electrons, it's a helium atom, basically. But when it's first spit out by this process as a cation, as He4, as a helium 2+, that's what we call an alpha particle, is the cation. And it will gain electrons eventually.
So like in a test, if we're given to find what it forms, we'd be given that uranium is an alpha particle.
Oh yeah. So on the exam, the question is on the exam, how would you see this? Like using this equation as an example, we could say what nuclide is produced when uranium-238 undergoes alpha decay, and you could figure out that it must be thorium-234 the way we did. Or I suppose you could ask the opposite. You could say, to make it a little spicier, which nuclide would undergo alpha decay to give thorium-234? And if this were the unknown, you say, okay, so what gives helium-4 and thorium-234? It's almost easier, right? There's no subtracting to do. Now it's 234 plus 4 is 238, 90 plus 2 is 92, 92 is uranium. So we could ask it either way. But yeah, we haven't gotten yet to predicting which decay mode, but we could also ask, which decay mode is most likely for this or that. But for the alpha emitters, it's a little tricky, because as we'll see, there's the next one up here is a heavy one, but it isn't an alpha. So I'm a little leery of asking, ones that I don't know, try to stick to something that's more bulletproof as far as being right all the time. So alpha emissions, pretty common for very heavy nuclides, because you lose 2, right? Looking at the numbers here, you lose 4 from the mass number and 2 from the atomic number. You lose 2 from the atomic number, 4 from the mass number. So if we look at the number of protons and neutrons, that's 2 in each, right? We lose 2 neutrons and 2 protons. So on the graph up there, losing 2 of each, yeah, that's going to be an arrow that goes, down and to the left. We're going to go down 2 on the x-axis of protons, and down 2 on the y-axis of neutrons. So the alpha decay is going to go down to the left, and go down 2 and go 2 to the left. Okay, so that gets us closer to the band if we're way beyond the band. The problem is U-238 is probably up here somewhere, where if it keeps going down, 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 it's going to miss the band. It's going to wind up above the band. So we got to get back over to the band some way. And that's where this next decay mode is shown. So we'll get to that in a second. So alpha decay is the first one. The equation looks wild. You can't balance this for atoms like you would in Chapter 3, but that's okay. We're not balancing atomic symbols. We're balancing mass numbers and atomic numbers, which is fine. The other thing on the right there, it says 2. That's a gamma. That's a lowercase gamma. We'll get to gammas shortly. They do not affect the balancing, so it wasn't a big deal to have them there. They're there because that reaction does give off gamma radiation, and I wanted to put it there. That's something that I did. Maybe that's how I got the way I am, is exposure to radiation or something. Although we didn't have much actual radioactive stuff. In graduate school, I did enough of this with radioactivity and everything to be a fan of it. And so I'm a stickler for having the equations be accurate if I can. So, the gamma rays should be there. All right, now the next 3 things on this list actually all technically fall into a category called beta decay. But in Gen Chem textbooks, number 2 is what they call beta decay, and the others get other names that are technically fine. Number 2, if you've ever seen the more technically correct category of this or something, this would probably be called electron emission or something like that. All 3 of numbers 2, 3, and 4 are actually all under the banner of beta decay processes. But I'll play along with the Gen Chem textbook and say, okay, number 2 is beta decay. A beta particle is identical in every way to an electron as far as its properties. It has the same mass and the same charge as an electron. So what's so special about a beta particle? Well, it's similar to what's so special about an alpha particle. What's so special about an alpha particle? If otherwise similar to a helium nucleus, well, it came from a radioactive decay. And same thing with a beta particle. The beta particle, this electron, is created by the energy of this radioactive decay process. The decay process gives off enough energy that amount of energy is converted to the mass that makes up the electron, E equals mc squared, which we'll get back to again. People didn't believe E equals mc squared that much back in the early days of it, but Einstein's equation, E equals mc squared, where c is the speed of light, which is stupid huge, so when you square it, it becomes stupid squared huge squared. And when we divide to get how much mass this is, we see that when you divide the energy of the decay by stupid squared huge squared, you get a little bit of mass, right? When you have that energy and you divide it by such a large number, c squared, the mass is going to be small, but that's all right. It's just enough to be an electron. So relatively energetic decay process creates a tiny little particle, an electron. So the electron is created by the energy of the decay process and is spit out from the nucleus. So spits out the electron. Once emitted from the nucleus, it is identical in every way to any other electron you'd find anywhere else in the universe. But its origin is different. It's not an electron that's just found in a 3p orbital. It's created by the radioactive decay process and spit out. Now, thorium-234 here, we say, okay, that was produced by alpha decay of uranium-238. That's nice. Unfortunately, what do we know about thorium-234? It has an atomic number greater than 83, greater than that of bismuth, so it must be radioactive. So you can't reach the band of stability in just one step often. Thorium-234 is still radioactive. And it turns out, like I said, if you go alpha, 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 trying to get to the band of stability, you'll probably miss it. You're going to be above the band at some point. So we've got to have some way of getting to the band. So the thorium-234, it turns out, uses beta decay to get a little closer to the band of stability. Let's say we didn't have these numbers or symbols over here. We could figure them out, right? Given that an electron is -1 charge, we're going to use that as the atomic number. Notice the symbol here, okay? The electron, the beta particle, has a -1 in the bottom position. The bottom position is usually atomic number, right? But this is not an atom. This is a subatomic particle. This is an electron. But here's how we do it. Okay, the bottom number, the number of protons, that reflects the amount of charge, right? The amount of charge in the nucleus is the atomic number. Carbon has 6 protons in its nucleus, has 6 plus charges. So we're going to put a -1 in the bottom position for the charge on the electron. And then the top number, that's the mass number. To the nearest whole number, an electron weighs 0 AMU, right? It's not literally 0. It's a tiny fraction of an AMU. It's about 1/1800th of an AMU. But it's rounded off to 0 for the nearest whole number. So the mass is 0, the charge is -1 for the electron. That's where those numbers come from. And so we can use them in equation balancing. So what must the top number be? What plus 0 equals 234? 234, right? And the bottom number, this is the trickier one. The top number is stupid easy. The bottom number is tricky. This is the one that gets you if we're doing a beta decay. Something plus -1 equals 90. The by far most common wrong answer on this. Really smart people look at this and make the same wrong answer all the time. Careful, it's a -1. -1 plus something equals 90. So it's going to be 91. And by far the most common wrong answer is to say 89. And don't feel bad if you said 89 because you want to say 89 plus 1 is 90. But it's a -1. It's a -1 there, so it's a 91. Okay, so don't blow it because on the exam there's always a choice if there's a beta decay that has that error made. And a lot of people who otherwise get everything right all the time will blow it because, you know, they got tricked. It's an easy trick. Don't feel bad, but just don't do it on the test, okay? Practice yourself out of that. And balancing these nuclear equations, it's like playing piano or kicking field goals or something. With practice, you get better at it and you'll make fewer mistakes. And then 91 is PA. Well, whatever PA is. It's Pennsylvania 234, I guess, whatever it is. That's protactinium. Pennsylvania is not radioactive, although it could have been if 3 Mile Island had gotten worse. So that's oh no, that's radioactive as well. You're kidding me. Yeah, turns out that this daughter nuclide, the protactinium 234, it's radioactive as well. So that's going to have to decay by some process as well. But we're getting closer to the band. On the graph up here, if we were at the uranium-238, it's up here, it decays, goes down that way, and then we go down that way. So now we're getting closer to the band. So we got to zigzag our way to the band if we're uranium-238. We go down, back, down, back, down. So that's all right. We can do it. It could take more than one step. So be careful on your beta decays, okay? Careful on your beta decays. The -1 means you go up an atomic number, which is fine. We can handle it. We'll use another beta to get another alpha to get further down. Because that bothers people sometimes. They say, if you're trying to get 83 or less, why are you going up an atomic number? You went from 90 to 91. That's not helping. But again, like we showed with the graph there, if you only do alphas, you're going to wind up missing the band. You have to zigzag your way to the band. Nuclides that undergo beta decay are generally ones that have, so to speak, too many neutrons. High neutron to proton ratios. If you have too many neutrons to be stable, that is called neutron rich. Another way that's sometimes expressed, like in the textbook, it'll say it's proton poor or something, but we usually deal with neutron. on this. The next one, they mention being proton-rich in the text, which is kind of, we always focus on neutrons. So neutron-rich nuclide, if it has too many neutrons to be stable, it undergoes beta decay probably. Beta emission is another term. Either of those is acceptable. Because think about what's going on. We started with 90 protons, and how many neutrons in thorium-234? 144. And how many protons are in the daughter nuclide? 91, right? That's the atomic number. Duh, it must be 91 protons. How many neutrons in the daughter nuclide? 143 neutrons. So we have converted, in essence, a neutron to a proton, right? We have one fewer neutron, one more proton at the end of that reaction. So beta decay converts a neutron to a proton. And that's a good thing if you're neutron rich, if you have too many neutrons, which means you're above the band of stability. If you're above the band of stability, that means that your neutron-proton ratio is too high. If you're here, it's going to be beta decay, it's going to be beta emission. You're going to emit an electron from the nucleus by creating it, then spitting it out. And that will get you one fewer neutron, so you go down, and one more proton, so you'll go to the right. So beta decay is predictable for things that are above the band of stability because it moves you toward the band, makes a proton out of a neutron. Somewhere I still have that cereal box. It was years ago. Remember Jimmy Neutron? There was you know the cereal. I guess people do know Jimmy Neutron. After all, it's great. And you know, Oops All Berries, the cereal. Like there's Captain Crunch and there's Crunch Berries and there's the Oops All Berries, and those it's easy to eat a whole box of at a time, right? And they had a special version of the Oops All Berries that was Captain Crunch's Neutron Berries a number of years ago, and I saved the box. It was great. So I have Neutron Berries. I saved the box. I know it seems stupid to save the box, but. So I'm surrounded by neutrons. There are no by the way, there are no neutrons in the box. I checked. I was very disappointed. When you open the box of neutron berries, no neutrons, no berries.
Is that a good thing?
What's up with that? I don't get it. It's like Jerry Seinfeld's grape nuts bit. You open the box, no grapes, no nuts. I mean, it's the same thing. So fortunately, the neutrons are not falling out of the box. That's good. But I just realized that I still have the box. Now I have to find it and bring it in, probably, right? All right, now. The other kind of decay that we haven't addressed yet, we've dealt so far with what if you're above the band or beyond the band. What if you're below the band of stability? What? Got something for that? Sure. We got something. Positron decay is one way of addressing that. Positron decay involves the emission from the nucleus of a positively charged electron. What? Oh, now he's just doing crazy talk. Positively charged electrons. Now, somebody increase his dosage. What? No, they really, get Diet Mountain Dew to the lecture hall, stat. Get a needle and a bag, and we'll put them on a drip. Positively charged electrons, this is insanity, right? But this really does exist. They don't last long, but positrons are literally positively charged electrons. They have the same mass, but the opposite charge. They have a positively charged electron. Same quantity of charge with a positive sign. And the positron is created in the same way that the negative beta particle is created. The energy of the decay process divided by c squared, that gives you a mass. And that positron is spit out by the nucleus. Potassium-38 is a positron emitter. It turns out that when it spits out the positron, let's see, that's 0 and +1, right? 0 mass number, +1 charge. So the daughter nuclide would be argon-38. Mass number stays the same. Atomic number goes down by 1 because we lost a positive charge. So 18 is the new atomic number. So what we have done here is gone from 19 protons, 19 neutrons to, let's see, 18 protons. Which order did I write them in, I guess? It's hard when they're both 19 and remember which order you're writing in, even though it's right there. 18 protons, 20 neutrons. There we go. We've converted a proton to a neutron. Think about it. If you had a proton and you could somehow shed the positive charge without losing much mass, what would be left behind is something with about the same mass as the proton, but with no charge. That has a name, neutron, right? About the same mass as a proton, but neutral. It's a neutron. So positron emission is common when you have so-called neutron poor nuclides, low neutron to proton ratios. That would be below the band. If you're below the band, we would like to convert a proton to a neutron. So we'd have one fewer proton, one more neutron. So we go to the left and up. So positron decay is common when you're below the band. So now at least we have one thing for each, right? Alpha if you're beyond the band, beta if you're above, positron if you're below. So at least we have 3 predictable modes of decay. There are others. But the positron is the so-called antiparticle. Heard of antimatter? Heard of Mr. Scott on Star Trek? Captain, you can't mix matter with antimatter. She'll blow up. Well, yes, that's true. Antimatter is sort of the mirror image of matter. It has negatively charged things in the nucleus and positively charged ones outside and all those things. They would zap each other and become energy. And we'll deal with that if you've ever heard of a PET scan. That's what's actually involved. But positrons are antimatter. They are the antiparticle of the electrons. They are the anti-electron. Similar in every way except charge, where they're the opposite. The problem with positron decay is creating that particle. This last one that we want to, if I can get to at least this next one, that's fine. Creating the particle. What if you have a decay process that is for a neutron-poor nuclide, but it doesn't have enough energy in the decay process to create the positron? Turns out that number 3 and number 4 accomplish the same goal. Number 4, called electron capture, achieves the same goal as positron decay does. It decreases the number of protons. It increases the number of neutrons. It's also possible when you have a neutron-poor nuclide. It involves sucking in an inner orbital electron, like a 1s or 2s electron, into the nucleus. Almost done. It's a slow process. It's a very slow process. It only is generally seen when the decay by positron emission would require too much energy to create the particle. Like it's an exothermic process, but not exothermic enough to create the positron. So instead, we do this. Mercury 194 is an example of an electron capturer. So this has a reactant, right? Here's a second thing on the left. So far, we haven't seen 2 things on the left. So this electron is from 1s or 2s orbital near the nucleus. Nucleus sucks in the electron. And then balance the numbers. 194 plus 0 is 194. 80 plus negative 1 is 79. Ooh, 79 is gold. Oh, how exciting. This is great. We can do this reaction and send it into cash for gold, right? Bummer about this. Gold 194 is radioactive. Darn. The only stable isotope of gold is gold 197, as you can see. It says 196.9 something. Gold 194 is radioactive. Because the alchemists, remember the wizard hat and velvet robe crowd that would try to do crazy stuff back in the Middle Ages? This is the alchemist's dream, right? We're turning mercury into gold. I mean, this is spectacular, right? Unfortunately, the gold 194 is radioactive enough that it wouldn't make it to cash for gold, even by FedEx, in time to get the check. So, unfortunately, that doesn't work. But that's okay. So, we got a few more coming up the next time. Read along. The problems are posted. The connects are posted. Good. But practice balancing some equations if you want before the next time. That's something that takes a little practice. And we'll do better the next time. So we'll see what happens.